So I work for Canonical, and we have a product called Juju, which we are in the process of transitioning to Go. If you came to Google I/O or you saw Google I/O, you would have seen our architect Gustavo talking about. Gave a little bit of talk about it. I'm not going to give much more of a talk about what actually is Juju because I'm not trying to sell it to you, but I'm trying to use it to demonstrate how we're developing in Go at Canonical. About me, I'm a contributor since February 2011. I do a little bit of work with AGL on the SSH package. Also work very interested in ARM, so I spend some time working with Marnex there. I run the ARM5 builder at the moment. I've got a bunch of junky ARM hardware sitting under my telly, which runs the builder. And I joined Canonical just a couple of months ago to work for Juju. So this is the producty bit. What does Juju do? It is a service orchestration platform. What does that mean? Juju talks about the relationship between services and their relationships together. And a service is MySQL, WordPress, something like that. It is a framework for system administrators, for developers, for anyone really to write these relationships with what we call charms. And charms encapsulate the logic of what you want to do inside hooks. And hooks are really just shell scripts. So this is all just a framework to pass information between services. And I'll talk a little bit more about what that actually does. But the key thing is that Juju is a framework for managing a very large distributed environment. And we have many agents spread out across this environment which have to coordinate together. The components of Juju are a centralized state repository. That's currently Zookeeper, which is don't know if I can't actually remember who wrote it, but it's essentially an in-memory file system. And one of the things you can do with that is that you can watch paths on it. So the agents in the system communicate by just observing changes in this file system. And we mutate the system, we add services to it by just writing them into this file system. There are 3 or 4 major components. The first one is the provisioning agent, and its job is just to watch for new machines being added. And it then talks to an infrastructure provider like EC2 and says, make new machine. On each machine that has been made, there is a machine agent, and its job is to handle starting and stopping various services that are put onto it. And each service is represented, each instance of a service. So you might have the WordPress service, and there'll be multiple instances. If you've got it spread across multiple machines, is a unit of that service. And so there's a unit agent, and that's actually responsible for starting and stopping the service, running the hooks. So a hook is essentially when you establish a relationship between a service. You say this MySQL service is related to the WordPress service. All of a sudden, the information about the WordPress service is available to MySQL and vice versa. So the charms then have this information to, on the MySQL side, add the database user, and on the WordPress side, to add the database host so that they can all be hooked up. It's really just a framework for managing the configuration via these hooks. There's a bunch of command line tools which we use on our side to kind of change it. In the Juju world, we call OpenStack a provider. So EC2 is a provider, OpenStack's a provider. The provisioning agent is the one that really interacts with the provider. It says, make a new machine, stop a machine. Command line utilities on the other side, which are really used by the charms, and the charms themselves, which Canonical write. We had a thing at the last UDS called the Charm School, where we encourage people to write charms, and they're really a way of encapsulating the best practice for installing WordPress or running a MySQL service. As I said, this is not really a talk about Juju. You can ask me more about it later. I just wanted to give a bit of a background about that. There are all these different components in it that have to interrelate through this central state. Juju is in, it's been shipping since 11.10. It's a supported part of 12.04, and that's an implementation that was written and developed in Python. Uses Twisted a lot of generators and callbacks, a lot of yield. It works really well. Like it's going to be supported for the life of 12.04. But it's quite hard to get right and quite hard to reason about. A large test base, and it's heavily asynchronous, and it's hard to know when you've made an action. If you've written something into the state, you've said make a new service, and that's really just creating a bunch of entries in this file system. When they've been actioned and have they been actioned, it's quite hard to know in the Python code. The reasons why, there are many reasons, but some of the main reasons why we've chosen to transition it to Go are the watcher pattern is a really good way of encapsulating this. Watch this file system and tell me about the changes, rather than pass the callback function and it will fire when something is changed and you have to filter out a whole bunch of changes. We can literally open a watcher, and I've got some example code of the watcher later, and it will give you the path you're interested in, and a typed thing, not just a string. To explain, as I said, there's a lot of callbacks in Juju, and in moving to Go, we're able to make all that code much more top-down, much more synchronous. The interactions with this state are encapsulated in just one package, and in Python there's a lot of passing callback function, getting called, maybe attaching some data to that. In Go, it's much simpler. We say state get machine, and we just get a machine object back. Now, of course, that might block some network data happens in time, but that's all taken care of by the Go concurrency model. Obviously, static typing really helps us reduce a lot of errors where you gave us an int when you meant a string, that kind of stuff. The binaries have a low resource footprint, and that probably needs some qualification. Because Juju is involved in making virtual machines in the cloud, we actually distribute the Juju tools, the agents, the binaries, just stuff them into a zip file and put that on S3. That's about 5.5 meg, compared to having to do an apt-get of Python, Twisted, all the other dependencies that it needs. So it's a lot simpler for us to work with, especially as we're developing, it's a lot simpler for us to work with these tools because they're just a single binary. Go is supported on ARM. That's kind of an important one from Canonical because we have a relationship with various ARM providers. So Caldexia, who make this wonderful ARM server, like ARM, Canonical is very committed to ARM, so goes a good fit there. And lastly, Canonical is very interested in Go as a language. Juju's the first, but not the only one of projects that we're using it for. So a little bit about how we develop. We've a team of 7, as one manager, and six people were distributed across the planet. Myself in Sydney, our boss who's in Ann Arbor, Michigan, Aaron who lives in Romania. We've got 2 guys in the UK. We've distributed all around the world. So we use Launchpad for project management, managing our releases, managing our bugs. Lots of discussion on IRC, lots of discussion on the mailing list. We do a weekly Google Plus Hangout, which had to be put back 2 hours for this event. And we do occasional week-long sprints. So we were, last month, we met up in Europe, locked ourselves in a hotel conference room, and just hammered on Juju for a week. Those are fairly infrequent. Like most teams at Canonical maybe will have one of those a year, because obviously they're quite expensive.
Where did you say you went to last time?
We went to Lisbon. It was awful. It was awful. So we use Rightfold for code review, and we actually use that via a tool that Gustavo wrote called LBox, and that's wraps up the interactions with Launchpad of setting a review, doing the merging, and kind of ties that together. So we'll use LBox to propose a change that actually opens the code review in Rightfold. We do all interactions with that, and actually do a submit via LBox, which closes all the Launchpad stuff. We, obviously being Canonical, we use Bazaar, and BZR is not that friendly to a GoPath environment because you need to, every branch has a different name, and it's very traditional to check them at, /trunk, /this branch, /that branch, which plays havoc with a GoPath environment. So Gustavo wrote a wrapper called CoBazaar, and when we switch between branches, it literally just swaps one out for the other, so they stay in place. As long as the branch is clean, it commits it privately, stuffs it into a location, puts your other branch there. As well as writing Juju, we've had to write a whole bunch of other supporting libraries, GoAMZ for interacting with Amazon, GNU Flag, GoYAML, for legacy reasons, because a lot of the data structures in Juju were in YAML. So as much as we don't like YAML, we've got to interact with it. And GoZK, which is the Zookeeper wrapper. And that's the only bit which actually uses, GoYAML, both GoYAML and GoZK use CGO. But everything else is pure Go. We are moving to MongoDB. I'll come back to that. A variety of editors, pretty much everything from Sublime Text. We've got two guys who use Acme. Vim, they're all well represented, and a variety of GoPath strategies as well. Like I just have one GoPath. I know Frank has one for Juju and one for his third-party code, which is higher in precedence. I know William doesn't bother with any of that nonsense. He doesn't bother with CoBazaar either, and just moves branches into the right spot. I don't know if he still does that. For testing, we use Gustavo's GoCheck library pretty heavily because we're not just doing unit test stuff. We actually have to test at pretty much most of the package levels, at least bring up a Zookeeper, put some stuff into it, run an agent against that. So GoCheck gives us most of that scaffolding. That also gives us a bunch of nice helpers as well. Lots of table-driven tests. You get double internet points if you use a table-driven test. And another part of using GoCheck is there's quite a lot of patterns where we will embed one test suite inside another to use its setup to then build a more complicated setup to test a larger piece. We also have a thing called Juju Test, which is a harness which tries every provider. So we have this thing we call the dummy provider, which is just a mock. We have the EC2 provider. We have other providers that we're writing, and it tries the code base against every one of those combinations to do the same things, to make sure that we're not leaking any "this only works on EC2" kind of stuff into it. And the last one is we do a lot of testing in _test packages, which is a little bit, coming from my experience with the standard library, it's a little bit different. We do that mainly so we don't cheat with private symbols. And we ran into one interesting problem where we couldn't use main _test. Well, we could, but it worked 90% of the time. I can explain why it doesn't work later. We were doing it wrong. So this is a little example of how we compose test suites together. Machine suite, GoCheck, you'll put your test on a type, and so these types were traditionally called suites. And this line actual suite actually introduces that to the testing framework. So somewhere inside this package will be one line called test package, which just kind of is the link that joins GoCheck into the standard testing framework. ConSuite actually is a composition of a few other things, but that actually builds for this test package a zookeeper running on an ephemeral port that's set up ready to go. So whenever we say set up test, we have a zookeeper ready to go, which is important because we run like on this machine you'll run 4 in parallel. Some examples of the kind of nice features you get with GoCheck: you get assert and also check. Generally, error is nil. These are done by importing the package at dot, which is otherwise, yeah. It's just the way we do it. And ID equals, and that can be pretty much everything, but except for maps where deep equals. So if you say equals, it will do an equality. Oops. If you say deep equals, it will do every item in the actual map matches the expected map. These last 4 lines were taken from the status command, which produces a huge blob of YAML, which we then have to compare to our test blob of YAML. And rather than comparing it as strings, we encode both of them into we basically marshal them back into a map of maps, and then just do the 2 maps, are they equal? And the last one is it gives you pretty error messages when things go wrong. So in this case, error matches is actually the one on the right is a regex. So you can have you can supply a regex to say, does your error match this regex? There are other nice variants that if you don't have a match, it will print out on the screen the quoted version, which is really useful if you're trying to test the output of something with a lot of quoting and strings and curly braces and things like that in there. But if it doesn't match, you can just copy the whole thing into the test. The error handling, because this is such a big asynchronous system, we have to expect that most things will fail. And we have to check all the time all our error cases, and then most of the time we actually just quit back up to a known state. But the ability to have those errors all the time is very important. And you asked before about Mongo. Currently, whenever we work with a document in Zookeeper, pretty much every operation goes to Zookeeper, so every operation can fail, so there'll be an error on it. That's pretty tedious to work with. So as part of moving to Zookeeper, we're batching the reads and writes so that most of the methods that we have on a document will now not return an error, because it'll have, if we get it successfully out of Mongo, then we can work with it. And the first time we'll have an error condition is possibly when we try and put it back into Mongo. I put this slide in not because I remember thinking about a month or 2 after I joined Juju, yes, I know exactly what everyone is complaining about, the noise of having to write if error, if error, if error. But after a bit more consideration, it occurred to me that it wasn't the fact that we have to check the error all the time. It's the fact that we've written our code in such a way that we're always exposing the error. We're never constructing code that not cannot fail, but the state package we have, which deals with Zookeeper, because every operation goes to Zookeeper and gets something, could fail because of network error, could fail because of whatever Zookeeper's problem. So it was in our construction of this library around Zookeeper that we not made it in such a way that we always had to deal with the errors constantly, rather than this caching model which we're moving to with Mongo, which says, get the document, do whatever changes we want on it, which obviously can't fail because it's in memory, like we're just changing fields, and then try and put it back. The last one is using Gustavo's tomb package, which is, does anyone remember his post about it? Has anyone heard of the tomb package? So The thing we use the tombs for is obviously we have a lot of agents which we fire off and process, and then they go off and do their things, and they're reacting to changes they see in the state. And one of the important things is if they have an error, we must stop them and start a new one in their place. One of the restrictions we have is that these agents run under Upstart, and Upstart has a kind of limited number. Like if you just say, right, we'll just panic, process will get restarted by Upstart. Upstart pretty much gives you about 3 goes of that within 5 minutes, and then it will cut you off for a while. So we have to deal with, if we decide, right, an error has occurred, we want to collapse back and reconstruct, make a new connection to the state, and start over again. We have to do that in process. And so the tomb is really important for us to be able to tell any going routines we have running that process, please exit now, and more importantly, wait for them to actually exit. And pretty readable. This is an example from one of the watches, and the key thing here is inside the main loop where it's getting watch events from another go routine. At any time, we can ask this watcher to exit by using the kill method is actually exposed to a user of this watcher. So at any time we can say, please stop, and this channel will become closed, so it will always return, and this thing collapse back up. At the same time, if we have an error while we're using it, we can, rather than just maybe print this error out to stand it out or something like that, we can pass this error into the tomb, and again it will collapse out, and we can wait for the process to exit and capture that error rather than just kind of shoving it on to stand it out. Okay. So, would you like to ask any questions?
It's a hard act to follow. I'm not sure if I have any funky Meetup integration code. Anyway, so I'll be talking about 2 very simple programs. One is called StatHat line counter, and the other is random password please. So the audience is really, I guess, beginning Go programmers, just to show how you solve a simple problem in Go that, and then in particular compare and contrast it with how you might solve it in a more conventional language like Python. And Python is an excellent language. It's been my language, it's basically paid my bills for the last decade and then some. And yeah, I'm the founder of this is a small startup called SlickDNS, and I wrote that using Django, which is a Python web development framework comparable to Ruby on Rails. I don't think it's too controversial statement. Before that, I did C++, and before that, I did COBOL. No joke. Although I have removed COBOL from my resume for many years. Excuse me. Yeah, I'll talk about the shirt. I'm Canadian. I've been here in Australia for about 1.5 years. Before that, I was in California for 4.5 years. Again, working predominantly in Python. I worked for a company called Lowry Digital. I did image restoration of most of the classic Disney archive. So if you have kids and they watch Jungle Book, I helped in the restoration of that. We also did James Bond, Star Wars. While I was there, I developed a distributed file system to help in the processing of those films. So we had a compute cluster of 500 Mac towers, heavy suckers. So you can imagine 500 Macs simultaneously hitting a file server with a single gigabit connection would very quickly kill it. So I developed a system to basically stripe files across 40 plus file servers using basically FTP. My last job in the States was at a financial management or investment management firm, basically doing bond management cash flows on subprime RMBS. So yeah, it's pretty much as boring as it sounds. So I moved to Australia. Anyway, so at that company, I developed a grid compute system, again, using Python. So basically, you could essentially take more or less an arbitrary Python function with effectively a tuple of inputs, and then it would distribute them across a compute farm, and then return the results back to the calling process. So it worked pretty well. So again, I'm a fan of Python, but I think there's there's some niches that Go can fill, I'd say, in the gaps for the time being. But I think going forward, I see a bright future for Go. Okay, so StatHat line counter, dead simple log file statistics. So SlickDNS basically is a DNS hosting service. So let's say you have a bunch of domains and you want to manage the DNS for those domains. I can do that for you. So I have 4 DNS servers across the world, and I want to log the number of DNS queries served every minute for each DNS server. But it's general purpose. So basically, any log file you tail to the standard input of StatHat line counter, and it will log the number of queries or number of lines read every minute that's configurable to StatHat, which is basically a statistics service, so it makes nice charts for you. Coincidentally, StatHat is written primarily in Go. I think at the Go I/O conference, Patrick Crosby was on a panel of Go users. So a good talk. Okay, so the inputs, your log file, in my case is TinyDNS, which is a DNS server, and the inexorable march of time. So really this is a concurrent problem, right? You can imagine you have your clock ticking away in the corner, then you have your log file, as queries come in. And at the bottom, it's hard to make out, but that basically is it's a graph of all the queries for one named server in a 24-hour period. And it's around 500,000, give or take, per name server. So around 2 million queries per day across all 4 servers. For 99% of those queries are from 2 BitTorrent hosting sites. I'm sure it's perfectly legal, but it's one of my customers. So it's a very busy site. So it's quite interesting to see the lines go by. So this essentially is how we solve the problem. How do you log lines read? So read lines are bolded. That's a function. It basically returns a channel assigned to the variable line counter. Tick is another channel that's given to me by the built-in library called time. So basically, I'm asking it every 60 seconds, I want you to send me an event on this channel. N is my counter. Then I have an endless loop. I select between the 2 channels. So whenever a line comes in, I increment the counter. And then whenever 60 seconds elapses, I then log that value, and then I reset it to 0. Does that make sense to everyone? If this reads like C, pretty much, except select, it looks like a switch syntactically, but you can think of it as a select. I presume it's intentionally modeled on the select Unix system call. So basically saying if any of these channels has a value to send, then give me that value. In this case, I don't actually care what the value is. Right, I'm just throwing away the value. I mean, all I want to know is a line is read. I don't care what the value of the line is. And the tick channel will actually return the timestamp, but again, I don't care because I know it's 60 seconds. Okay? Anyway, to my mind, it maps very closely to the description of the problem. Right? So basically, every 60 seconds, you want to log the number of lines read, and every time a line is read, you want to increment the counter. Right? So, and read lines. This is a little trickier if you're not familiar with Go. That bit in the middle, I think that is a anonymous function literal closure. Am I correct in that terminology? Right, so by calling this function, you return a channel. The channel is basically, you can think of it as a typed, I don't know, yeah, a typed pipe, essentially, if you're familiar with the concept of Unix pipes. So this just returns Boolean values. Again, I don't care what the value is. It's always set to true. So basically, it's an endless loop. I read standard in. I read the line. Again, I don't care what the value is, so I set it to underscore. I'm leaving out the error handling. As it happens, I just exit. But for me, it's safe because the program's running under daemon tools. So basically, it's restarted if it dies for whatever reason. So essentially, call that function, again, it returns the channel. So it's a closure because notice I define the channel outside of the function literal, but then it's returned as the value of the function call. So the interior function literal basically keeps that, keeps a reference to that channel. So it's, again, think how would you do that in C++ in terms of reference counts and so on? It's a bit tricky. So that basically is it. You just put those two things together, and it just sits there and day in and day out. But then with StatHat, you can set. I get a report every day telling me how many queries have been handled. Then you can also set reports thresholds. So if it goes above a certain amount, hopefully you're not being attacked. If it goes below a certain amount, it would suggest something's up with the name server. Okay, so it's oops. I can more or less make it out there. So solution is very simple, but it makes natural use of concurrency via channels. But notice that the Go routines, quote unquote threads, they work in the background, so it's not explicit. As it happens behind the ticker, there we are, behind the tick channel, there is in fact a Go routine sitting there. But that's, it's not explicit, it's just working there for you. The same thing with read lines. The fact that it kicks off a separate Go routine is almost an implementation detail. So if you compare, if you have a Python background, for example, and I do, and in fact I did write a very similar solution in Python to the same problem, except I was logging stats to the Amazon Web Services CloudWatch API. But it's effectively the same thing. So in Python, basically, you can imagine in the main thread, you're basically reading lines, but then you kick off another thread that runs in the background, and every 60 seconds, it reports N to CloudWatch. But then it's a bit trickier because the thread has to, if you want it to be accurate, you sort of have to account for the time it actually takes to log that value. So you set a T1, then you log it, then T2, subtract it from 60, and then you wait for that much. But then you have to explicitly restart it. So it gets a bit fiddly. Although another way you could do it in Python, because Python does have the notion of queues, which are very comparable to Go channels. But the problem is in Python, you can't select between, as far as I know, you can't select simultaneously between multiple queues. Well, because Python's dynamic, you could send multiple events onto the same queue, but then you'd effectively have to do a type switch on all incoming events. So I've done that type of programming in Python. So it gives you a coroutine style feel, if you like, but it's not, I wouldn't say it's idiomatic. So anyway, it's a very simple problem, but a very simple solution. And to my mind, a very elegant solution. Like it just fell out naturally. And it runs, it's efficient. The memory usage is stable. I don't have to worry about it blowing up and taking down my name server. Okay, the second program. Random password plays. It's a toy, but I think it's a good example of various features that come with a stock Go installation. So in previous life I installed websites. So you're installing a new web server and you need a randomly generated password, which if you're good sysadmins, you will store in the in-house wiki. So solutions, you can sudo apt-get install pwgen, or it's boring, or if I find you can write a random password generating web server in Go, which is what I did. So I won't show you the source, it's online, but it illustrates basic file I/O, how to write a simple HTTP server in Go, Go routines and channels. So essentially, Go channels, they're unbuffered by default, which means they block until the value is read. You can also create buffered channels. So in my case, I create a buffered channel. I can store up to 10 passwords. So the idea is, in practice is not an issue, but if it were computation expensive to generate a password, you could generate a whole bunch up front, and then it could serve them. So basically, when someone requests a password, they don't have to wait for one to be generated. In practice, again, it's not a big deal. But in the real world, if you had actually something computationally expensive, that is something where a buffered channel would actually help you out with. And signal handling, it's actually a bit tricky. This is my implementation of random password please. I want, if these web server is controls, killed by Control-C, I want to save the number of passwords generated to a disk file. So basically, in that case, you want to watch or catch Control-C signals term or whatever, the equivalent, and save that file and then exit. This does not illustrate use of best practices for generating secure passwords if you haven't worked for the NSA. Because I posted this at the Go mailing list, and all these crypto nerds come on and say, oh, blah, blah, it's quite funny anyway. It's like, well, or maybe you're tracking passwords. So then what, I hack into the server and I don't know. I was just trying to come up with use cases for their paranoia. But, it's primarily a example program. In my case, it's also marketing for SlickDNS. That was actually the real reason for writing it. So benchmarks. This is on a single core. So Go programs can run concurrently. I think by default they don't, or in parallel. Unless you explicitly say run n threads where n is the number of CPUs, it won't actually run in parallel. But I think this is indicative of the performance you can get out of essentially unoptimized code. So I ran, Apache Bench AB 10,000 requests to random password please, 2,500. And then if you run 10 in parallel, it bumps up to a little over 4,000 per second, which is pretty darn good.
Also, Apache Bench is really broken,
right.
And so those numbers are actually what?
Yeah, and obviously it's on the same machine since you're hammering local hosts. But the point is that Go out of the box probably did the C10K, right? In terms of serve 10,000, give or take, static requests per second. Which for so for a non-Node.js implementation, I say that somewhat facetiously, that's very impressive. The source code, StatHat line counter, random password plays. There's the live website, and Go, of course. So conclusions. Go, it's a young language. I guess it's 2.5 years old, officially or publicly. Yeah, but it's by no means immature. Yeah. I mean, if you know anything about the people behind it, you can understand why that would be the case. Yeah. Well, I mean, you have the great Ken Thompson, obviously, himself, and Rob Pike, and even Russ Cox. He's probably not as well known, but I knew him from having followed Plan 9 for several years. I think he was like working for Bar Labs when he was like 16 or something, right? So, yeah, code writing machine. So Go makes it almost trivial to write concurrent code. As I said, I mean, it's the somewhat trivial example, but StatHat line counter. I mean, it's a real world use case. It works for me. It does the job, and it's a concurrent problem that maps very nicely to a concurrent solution in Go. And increasingly, concurrent code, I think, will become more important as hardware scales out rather than up. Because chip speed, clock speed hasn't increased essentially in the last 5-6 years. I mean, my i5 is probably slower than my last P4 in terms of raw clock speed. Rich production-ready standard library. I ran a password please again using stock. It's built in or standard library, including the HTTP server. I mean, I've seen this discussion in Hackneys and elsewhere. Oh, I'm waiting for the standard library to bulk up. It's like, well, what are you missing? I mean, as a Python programmer, I would say the Go standard library is at least as rich as what you get in Python. And in some ways richer. For example, there's a lot of crypto built into Go, which really is not in the standard Python library, primarily for performance reasons, because for that crypto code, you basically have to bail out to C for Python to get decent performance. Whereas in Go, it's pretty much straight Go with a tiny bit of assembly here and there. But certainly they do not have to bail out to C to get good crypto performance from Go. Go also has an image library. I think Nigel can tell us about that, which is very nice if you've, like me, have struggled to install PIL for Python. I don't know. I'm missing that bloody JPEG library, right? I mean, it's nice to have it built in. And then a production-ready web server in Go. I mean, Python does have a built-in web server, but there's no way I want that out on the open internet. And I wouldn't be doing 4K plus requests per second, I can guarantee you that. So, easy deployment. Go compiles the static binaries, so you can literally SCP and you're done. Now again, if you deploy any sizable Python project, which I do, because you develop locally and then you push it up to your live server, and if you forget to install some third-party package, then bad things happen. With distributing code, all you need is a URL for the repository that you do not need to explicitly package it, which again, if you've done packaging for, say, Python or Ruby, it's a pain because you have code that works, but then you have to come up with this magic file format to put it out there on PyPy or whatever, right? And you only do it every 2 years, so you have to go and look up the reference again to figure out what the format is. But Python is basically the code. The code I'm running is the code I release or I distribute. There is no package format for Go. That's a feature. Right? People keep complaining, oh, I don't know, how do I pick a version? It's like, well, don't change the API. I mean, right? It comes up every so often in the mailing list. We need this feature and that feature. But to my mind, please don't change that. Right? The fact that you can just publish a repository, that is what you distribute and you're done. Is a very nice feature. But again, Go can't compete yet with frameworks like Django, although obviously there's some Go App Engine folks here. It's probably the most complete framework in the Go world. But again, Django probably came out prior to Django. I did Zope. I know I'm aging myself. But Django came out in 2005, 2006, which is probably 5-6 years after Python hit the mainstream. If you think Python came mainstream, maybe 2000, 2001. And it was first released in 1991, give or take. So give it time. I mean, it's not that Go is incapable of doing that. It's just a question of, of time, frankly, not ability. So do I have some more slides here? There we are, random hash replays. I don't know. There is an API if you're interested. You probably aren't, but so basically, asynchronous. It doesn't load the whole page. It just calls the URL and returns a password.
What is the profit part of your presentation? You have a log processing service and a passive generating service. Sell subscriptions
Yeah. Anyways, I use a couple of other Go services actually for SlickDNS. One is, here's the service. So if you update your name server information, then you want to push that out to the name servers as quickly as possible. That is actually done using a bunch of Go, they're actually web servers that run on each name server. So basically, the main app server pings the name servers and says, hey, the name server information has been updated. Then they turn around and call a HTTPS URL on the web server, which is essentially the latest version of the DNS data. So that happens typically in 3, 4, 5 seconds, which is not bad for government work. At the bottom, you might see a little counter there. That's the number of queries served. It's a bit of a gimmick, but I like it. I don't know if you can make that up, I don't know. It basically increases every time a page is refreshed. That works by every time a page is refreshed in the background, I spin off a little Python job that pulls each name server and adds them all up. Then that's the next value for the next time that a page is loaded. Again, that's just a little Go program that tails the name server log n+1, n+1 forever and ever. And so Go, I think, is very nice at filling the little niches. You can't do this in Python, but I think in a memory constrained environment, the fact that I know that Go will use very little memory, and and I don't have to worry about performance. I don't really have to worry about security. I don't think there have been any security releases yet for Go.
There have been, but they're only to do building in secure programs.
Right, okay.
Yeah.
And as it happens, I'm running Go behind Nginx. You just proxy it, you know. If Nginx is unsafe, then I think a lot more people are in trouble than me. So yeah, any back to the, I think that's it, yeah. Okay.
Can you tell me a little bit more about the signal handling?
All right, let's see if we can find the code here. I'm by no means an expert. I don't know that too many people can. Is that right? Yeah, there we are. Again, if you're interested, read the code. Where are we now? There we are. So this handles signals. Basically, this is a Go routine that runs in the background in random hash replays. So signal handling Go basically works using a channel. So you define a channel and you say, I'm interested in getting these types of signals, right? So in that case, I'm interested in kill, I'm interested in interrupt. And then basically block on the signal handling channel until a signal comes through. And then you do what you need to do. In my case, I'm saving the counter to a file, and then I exit. Okay. Again, I don't care in that case what the value is. Just one of those two values, and I need to exit. But you know, it's very nice. Yeah. But one subtlety is I probably should actually have the value of 2 there. I think if you don't have enough values in the channel to handle any signal that might be coming through, I think it basically kills the program, right?
I think it just drops signals.
Does it?
Yeah.
Yeah, okay, it just drops it.
It does a non-blocking send on the channel. So if the channel's full or it's not receiving, it'll just
Yeah.
drop the signal.
Even if it's interrupt?
Yeah.
Yeah, okay. Well, as always with signals, you have to be careful in any language, but anyway. But the point is in Go, it makes it nice and idiomatic. One nice little thing here is you notice save counter there. I call it synchronously. So there I want to block. But elsewhere in the program, where are we now? Here. So notice here I want to, just to be safe, every, say, 100 passwords that I send, I want to save the file just, you know, for whatever reason the power dies, right? Right. So in that case, I call save counter in a Go routine, right? So the point is I don't want to block the main thread. I'm fairly confident it'll succeed, so I don't really care what the error value is. So in that case, you call save counter in the Go routine, but down at the bottom, when you're exiting, you don't want, like, you know, you want it to finish before you exit. So there you call it as a standard function. So that's, you know, I would say it's a revelation, but it's nice that in Go, a Go routine is just a bog standard function, right? It only becomes a Go routine if you prepend it by calling Go, right? Again, think, say Python, it's a little more subtle. I mean, in Python, you can pass a standard function as the target to a thread, but there's a little more paperwork involved.
Thank you.
Yeah.
Essentially, this talk is about why we chose to do Go version 1 and what that means, and the process with which we used to get there. Go is a programming language, and I'm skipping these slides because you know what it is. So Go began as a 20% project at Google in 2007, and in November 2009 we went open source, and then we released Go 1 in March this year. When we started the Go project, we planned, like well before 2009, we planned for it to be an open source project from the beginning. And when we released it, it was released as a BSD style license. And to date, we have 28 committers from Google and elsewhere. And many people have joined the project, more than 200 contributing code or documentation changes directly. And since release, we've had nearly 10,000 changes committed to the tree. So it's a fairly high volume project. Our development process is based around Mercurial, and we have a plugin for the Rietveld code review system, which is a derivative of a Google internal system that we had that runs on App Engine. The Chromium team use it, and WebKit, and some other, the people at Canonical use it, as I learned this evening. But interestingly, for working with Mercurial, we actually use no branches in our development process. So everything happens on a change-by-change basis, and there are no deviations from the main line. So all changes are code reviewed, and they have to be approved by a committer and submitted by a committer. And we review them in public on the Golang dev mailing list, and that's been the case since launch day in 2009. We have a continuous build system that tests go across all of the supported platforms, the officially supported platforms. And the way we manage kind of contributions is we, unlike some projects like the Linux kernel, where they say, shut up and show us some code. On the contrary, we say, please talk to us about what you plan to do before you do it. Don't just go away and write a whole lot of code and then throw it over the wall. We want to be part of the process from conception. So there's a lot of planning involved in even smaller changes to the Go tree. So you can see that the project moves pretty fast. This is a graph of the contributions over time in 6-month intervals since launch in November 2009 up until April this year. And you can see that there was an initial kind of flurry of activity as I guess we fixed a lot of bugs that were reported on launch and rolled back a lot of foolish changes that David made. And then after that, we sort of got into a bit of a rhythm that gradually increased, and the proportion of contributions outside the core team at Google is growing faster than the rate of contributions overall, which is great. And particularly notable of those outside contributions are the Windows 3 BSD and the various BSDs and the Plan 9 ports are all driven by the community entirely. And I think Windows is particularly impressive. Our first non-Google committer was Alex Brainman, who sort of led the way on the Windows effort for a while. And I was just really impressed with how the community just kind of took charge of that whole thing and conquered what was actually a pretty savage beast. So a bit about managing the project. We have this continuous development process, and so since we have no branches, things break and then things get fixed. And sometimes the tree is in a better state than other times. We generally try and roll back things that break things, but sometimes something broke a few weeks ago and we just didn't notice because the particular issue wasn't being tickled by any tests or whatever. And so even though we have continuous build, it doesn't necessarily help all the time. And so we needed a way to provide stability for the users. And so one means to do that was with weekly snapshots. And so every week on a fairly regular basis, we would tag a particular revision that we thought was good. It was like, I'm going to tag a weekly now, don't check in that experimental change. And then we would apply a Mercurial tag and then write a change log and then send it to the public list and say, here's where we're at, you should sync to this weekly. And don't just sync to tip, just stay at the weekly tag until the next one. And this was great for early adopters and core developers, but it had some issues for just your everyday users. It became a burden to those users because they would have to update every week to stay in sync with the third-party libraries that they were using, and also to get bug fixes. And then it became, so it's annoying for them to have to update every week, but then if you let the weeklies kind of bank up and you fall behind, when you do have to update, you've suddenly got this big long list of changes you need to make. You need to go through all of the change log to see how you need to change your code and so on. And so you have these users who are at different weeklies, and then you have version skew between people with different libraries, and then that fragments the community, and it really slowed things down for a lot of people. And so by March 2011, we devised a release process, and that involved releasing a stable version of Go every 1 or 2 months instead of having a weekly every week. And we would pick the most stable of the past few weekly snapshots and say, well, that was a good one. We know that there was relatively fewer things wrong with that. And so that's our stable release. And then we would prepare a release notes that were like the must-read release notes where, if you use library X, you know this identifier has changed and so on. And so those were a relatively short list as opposed to the verbose weekly change logs. And then that made it easier for people. The users really loved it, and it kept the community much more in sync, because the first question whenever anybody had a bug was, are you using the latest release? And it's no big deal to update your code every 1 or 2 months. That was pretty manageable. But there was still skew, because a lot of the core Go community, and therefore the people who were most prolific Go programmers as well, the people maintaining some of the most useful external libraries, were still working at TIP or at the weekly snapshots, because they wanted to be using all the new stuff, and often they were contributing to the core, and you can't contribute on the release branch, you need to contribute to the TIP, because we only have one straight line. And so we ended up with a different kind of skew problem, which is you had the core developers and adventurous people using weeklies or TIP, and the general users using releases. Make it easier for everybody to stay on the same page, for everybody to be using releases. We introduced a tool called GoFix, which automatically makes changes to Go code to accommodate changes to the language and changes to the libraries. And we announced that a couple of months after announcing the release process. The release notes now mostly said this, that, and that changed, but don't worry about it, just run GoFix. And most of the time it just worked. There are some cases where it didn't quite work, but it wasn't. The important part is that it's not a SED script. It's not something that's textual search and replace. It was actually a syntactically aware source modifying program, source rewriting program. And so not only that, GoFix, it didn't just help the users, it also helped us as developers, because it enabled us to make sweeping changes to core parts of the language and libraries that would have seemed too daunting otherwise. We would have said, oh, it's going to take us a long time to do it to the core, and then our users are all going to have to accommodate this. And so there's kind of an inherent chilling effect to making any large scale change. But with GoFix, we said, well, you can just write a GoFix module to automate that change, and everyone will just run it, and it will be fine. And so this is a quote that we had shortly after the release of GoFix, which is somebody saying, yesterday he just GoFixed a bunch of third-party packages blindly, and he just recompiled and it worked. And that's, there's something pretty impressive about that, I think. But even with GoFix, it wasn't a panacea for these the version skew issues that we were seeing. Because the programming language is the root of the dependency graph, it's a really acute problem, version skew in a language. And so the fundamental issue was that the code that you write today will not necessarily compile tomorrow or next week or next month. And so as a result, there were lots of people and organizations that weren't ready to use Go because it was rightfully seen as too unstable for them. We realized that there was a need to stabilize Go and to move away from this system of constant change. And even though GoFix can fix a lot of things automatically, it can't do everything. And so we needed to sit down and say, what are the kind of changes, what kind of changes are important, and what kind of changes should we just stop doing? And so we decided to design and implement a stable version of Go and its libraries and its tools. And so this is where we come to Go 1. So Go 1 is a specification of the language and libraries that will be supported on the order of years. And importantly, it's available as binary downloads, which we hadn't done before in an officially supported capacity. And so it was really an opportunity for us to fix some irritations we had with a lot of decisions we'd made early on, to fix some inconsistencies in the libraries and tools, and to focus on fixing bugs. I mean, we'd been pretty good about fixing bugs, but we had amassed quite a list, and Go 1 gave us a really good reason to sit down and triage and condense that list. We'd also use it as an opportunity to design and build a proper tool set, a strong, consistent tool set around Go, which we it had kind of evolved before, but now we had a good chance to actually design it. And possibly most importantly, it was a great opportunity for us to say we need Windows support to be on par with all of the other operating systems, because it had always been kind of there, but it had never checked all of the boxes. And with Go 1, we saw an opportunity to do that. And principally, Go 1 is an opportunity for us to polish and refine what we had, not to redesign everything. It was look at what we've got, how can we smooth this out and make it as close to perfect as possible, and then release. So the planning process for Go 1 began with a proposal document that we worked on amongst the team, where we listed all of the things that we had thought about and proposed solutions to those problems. And there were many different approaches in several cases. And importantly, we prototyped all of those changes. Most of the major changes were actually fully implemented, or at least partially fully implemented within a smaller scope. Before we met as a team for a week to discuss the document in detail, to have a lot of arguments, and then form a coherent story, which we then presented in the form of this proposal document to the community. These are the things that we think we would like to do. What do you think? And so there was many senti threads occurred as a result, many very heated discussions and debates. And as a result of those discussions with the community and amongst the community, we made many changes to the proposal, adopted a lot of the suggestions, and had a really solid plan at the end of that process. And so the process of actually preparing Go 1 was to create a lot of issues on the issue tracker, and to categorize all the existing issues we had in terms of this is for Go 1, this is after Go 1, so just drawing a line in the sand in that sense. And then everybody in the community and on the team would just nominate themselves to do certain tasks. And this worked really well. We declared a moratorium on new features, which kind of kept getting pushed back until we finally declared a moratorium on the moratorium. And then we stopped developing the new features, prioritized stability, and you can see the process of that here. This is a graph of the number of lines changed each day in the months leading up to Go 1, and it kind of peaks at like 75,000 lines changed in a single day. And so these are obviously mechanical changes, but you can see kind of the breadth of the changes that we were making by this graph. And so, yeah, the largest of those changes were performed by the GoFix tool, and GoFix was really totally essential to this entire process, because we were able to try out changes and then refine it incrementally, and sort of, you'd be working on a GoFix module and apply it to a whole tree, see how it looked. And some significant changes were tried and actually totally abandoned. There was one change that we were that kind of prompted the whole Go 1 thing. Do we want to make this particular change to the struct literal syntax, I believe it was. And we ended up trying it, and it seemed just wrong. And so we backed out of it entirely. But the rest of the Go 1 process happened, so it was a win in the end. And so the GoFix workflow was really great, because we were able to still work in this straight line fashion, but prepare these changes that affected thousands of files and tens of thousands of lines. And the process was essentially, you would have two Go trees. One Go tree you would be developing your GoFix module in, and the other one you would be applying your GoFix module to. And then you would prepare the module, revert the second tree to the tip revision or head. And so you would have everybody else's changes all there. You apply your GoFix to the tree, build it and test it, and then if it runs, you would send both trees out for review. So you send the module out for review, and here's the effect of that module. And if somebody in the meantime comes in and is doing another similar change simultaneously, it actually doesn't matter, because whoever gets in first, the other one just has to resync, reapply the GoFix module, and everything just works. They don't have to go, oh my God, I just made all these changes and now we have to merge our trees and it's a nightmare. So this was an incredible boon for us in terms of productivity. And here's an example of some of the changes that were made by GoFix. This is changing the previous convention for error values in Go was an error type from the OS package, and then we changed it to just being a built-in error type. And this made OS not a dependency of most things, whereas previously it had been a dependency of everything. And so os.error was replaced with error almost everywhere. And not only that, there were built-in error types like EOF. So whenever a read ends, you detect an EOF or you compare it against EOF. And that moved from the OS package to the more appropriate place, which was the IO package. And doing all those rewrites with GoFix was much easier than trying to do it with SED, for example. Or even, it wouldn't have been possible with SED in some cases. So in terms of the public effect of the process, we stopped doing releases from R60, which was the last release of its kind that we did in August 2011. And the weekly releases, the weekly snapshots continued as they had before. And then, so this meant that R60 really started to smell by the time that Go 1 came along. But that was all right, it just meant that it was a soothing balm when Go 1 was released upon everyone. It was fantastic. But in the weeks leading up to the launch, we released candidates, which were basically weekly snapshots, but that were fully packaged in the way we intended to release Go 1, and encouraged everyone in the community to try them out. And we found and fixed a lot of issues in the process, and finally came out with a really solid Go 1 release for FreeBSD, Linux, OS X, and Windows. So just a little bit about what is in Go 1. So as mentioned, Go 1 is a specification of the language, and it's a specification of the libraries, that is their APIs, all method signatures, variables, constants, types, etc. It is a promise of long-term compatibility, so Go 1.x will always build Go 1 programs. If you write a program today for Go 1, it'll still build in years to come. Windows is first class. We have a new tool chain based around the new Go tool. And kind of subtly, it's also a change in the way the project itself is run. So some examples of language changes. We had a new rune type that represents a Unicode code point. And this is an important step in making the sizeless int, which is currently a 32-bit int on all platforms, but it will become a 64-bit int on other platforms, and that lets you have slices that are more than 2 gigabytes in length. You can have whatever int64 max is sized. And then we have the new built-in error type, as I mentioned, and that affected almost all the Go code that's ever been written. We defined equality on structs, so you can use like structs as map keys. And we also cleaned up some other stuff. We also made some API changes. We redesigned the time package to be much cleaner and simpler. It doesn't revolve around Unix epoch anymore. We regularized strconv, moving away from the old C-style API that we just kind of copied wholesale in the first place. We did a package reorganization, merely moving things around into appropriate places. Before it was all kind of flat and things were sort of hard to find. And we made many lesser changes. Oh, a little bit more about time. So the time package was based on the Unix epoch. The new redesign includes time and duration types. And so you now have a time that can represent a huge range of times with nanosecond precision. And the duration type represents an interval. So in the old fashion, you would say time.sleep and 2, that would actually be wrong. It would say that would be 2 nanoseconds, but it could look like 2 seconds. But the fact is you don't know what it is. But in the new time package, we have the duration type, and there are some constants like time.second, which represents a second in duration. And so if you want to say 2 seconds, you say 2 times seconds. And it's clear what that means. And similarly, if you wanted to print what time it will be in 1,000,000 hours, you'd say time.now.add 1,000,000 hours. And a nice little thing that fell out of this is we ended up with a new flag type, which is a time duration flag type, so you can specify command line flags in seconds or minutes or hours or so on. The package reorganization looked kind of like this. We had packages like ASN1, CSV, GOB, and out of context, it's not really clear what those mean. It's not really easy to see what they are or find them if you're looking for them. And so we put them in subtrees like encoding, Unicode, and so on. And all of that was automated by GoFix. We also cut a lot out. So there were parts of the standard library that we weren't happy with or that we felt were too immature. And so the packages that worked, but we thought were immature, we moved into sub-repositories of the main Go repository. They're still installable with the Go tool, but they're just not in the Go core, and so we don't have to be part of the compatibility guarantees that we made. And the unfinished and old packages were just left out entirely and not part of the release. And so I mentioned the Go tool. A bit of context. Before Go 1, you would build Go programs with make, so you would write a make file. But make files are kind of annoying, and for Go, they're actually redundant because Go was designed such that all of the information required to build a Go program is actually in the Go source itself. And so the Go 1 includes a new Go tool that removes the need for make entirely and just derives that information from the Go source files directly. So the Go tool is a complete build, test, and installation tool for Go programs. And here are some realistic examples. If you say go run hello.go, it will build and run the program in hello.go. If you say go build package, where package is the import path of a package, it'll just build that, that package. Go install will just install the package at the current directory. Go test, and a package name will test that package. And also, we hooked in some of our existing commands with the Go tool such that go fumpt would format a package, go fix would fix a package, and so on. Another nice aspect of the Go tool is that it allows you to fetch remote repositories automatically, because import paths and repository URLs are actually can be one and the same. And if they are, which is the best practice, you can just issue a go get command, and it will fetch that package, in this case from code.google.com, and then it will fetch any of its dependent packages because they will also be addressed in the Go source in a similar fashion. And so you get the all remote dependencies for a particular Go tree with a single command. And really nice around release time is that you could issue go get with a -fix flag, and it would run go fix on all of the source that it downloaded. And so in many cases, you could use older pre-Go 1 external libraries without having to actually make any manual changes to the code. A huge part of the process was documentation. We entirely overhauled, we went through everything, updated a lot of stuff, fleshed a lot of things out. We redesigned the website entirely, and so golang.org got a facelift, and we sort of rationalized how everything was laid out. We moved a lot of our blog content to golang.org. One really nice feature is we added sample code as a convention in test files. So instead of having a function test foo, you can have a function example foo, and that will actually document the identifier foo in your package. And so in the documentation, you get the code snippet presented. But when you run go test, it actually runs that example and checks against the printed output. And so your documentation becomes executable and testable as well. And to maintain the backwards compatibility guarantees, we wrote an API compatibility tool that essentially prints out the entire public interface of all Go libraries. And then every time a change is checked in, or every time the test suite is run, rather, the API compatibility tool creates another list and diffs it. And if there are any changes, then that's effectively a build error. And so that's a way of protecting ourselves from introducing incompatibilities as we go forward. We're currently allowing additions in point releases, so we're able to expand the APIs, but the API tool also gives us a view on how we're expanding the APIs. So in order to check in a change that adds to the API, you also need to check in a change that adds to a master list. And so it's very clear when you're making those kinds of additions. So where are we going? The goal of Go 1 was a stable and productive environment for people to work with. And now that Go 1 is out, we're really shifting our focus to using Go more than just developing it. And it's because it's only through using the language and using the stuff that we've built that we'll have a better idea of where to go with Go version 2. But with that said, there's still a lot of active development. Even though the design's locked down, we're working hard on stability, so finding and fixing bugs, and efficiency. There's been already, since Go 1, a lot of work on the garbage collector and code generation optimizations. We're looking at an improved scheduler and also just fixing hotspots in the standard libraries in terms of performance. And the code at TIP already performs, in some cases, 2 to 3x faster than it did in Go 1. So Go 1.1 will be a really substantial performance improvement release, and we're excited about that. We're also looking to broaden Go's portability. So the NetBSD and OpenBSD and Plan 9 ports that were present but deemed too immature for Go 1, we hope will be first class in Go 1.1, and we're looking to expand that further if anybody wants to volunteer. And also we're looking at adding new libraries to the core. Not sort of en masse, but there are certain things that would be really nice in the core, like an HTML parser, which we have, but it's just not 100% there yet. And also Unicode collation packages and some other smaller things. So far we've had 2 minor point releases, and they've just been issued to fix bugs. So the minor point releases are actually issued on a branch, and we just apply, cherry pick and apply all of the sort of smaller fixes, documentation fixes, and other critical fixes to those branches. And so we've had 2 of those so far, and we're looking at another major point release, starting to organize that at the end of 2012 and probably releasing in early 2013. As I mentioned, it will include code generation improvements, performance and accuracy improvements to the garbage collector, probably an improved scheduler, and many, many bug fixes. As far as Go 2 is concerned, it's likely years away. It's not something we're really thinking about right now. Yeah. And so, yeah, if you want to learn more about Go, golang.org should have everything you need, one would hope. And if you want to know more about sort of the Go project and motivations and philosophy, I highly recommend you check out this Meet the Go team video that from Google I/O, which was, I think, a pretty interesting discussion. And we had Ken there, which was great to have him speaking on record about the project. And yeah, that's all I have. So thank you very much.